So thus far we've focused really hard on the logarithmic function and what its graph looks like, but for the remainder of 6.4 we're going to take a closer look at the fact that it happens to be the inverse, and I guess kind of do some pretty easy stuff with it. So for starters, right, we know that the logarithm is the inverse of our exponential function. All right, and so another way to see this, or another way to describe it, is because if it's an inverse, it actually represents a power that we raise a base to get an answer. So here's, again, let me rewrite this. So we know that 2 to the 5th is equal to 32, right? That's our exponential way of saying that 532 is on my graph, right? If my input's 5, my output's 32, right? So we're talking about the function 2 to the x, all right? So the point 532 is on the graph. Logarithmically, we should be able to turn that around, right? Meaning that the point 32, 5 is on the graph, right? And what do we know about the inverse? Well, it's log base 2 of x. So what we're saying is that log base 2 of 32 is equal to 5. So again, notice that the function name is log base 2. The 32 is the input that I put into the logarithm, and what I get is an output of 5. Or said exponentially, 5 is the number I raise 2 to get 32. The logarithm represents a power that I raise the base to get that. We're basically saying that right there. So essentially, there's a two-way street, right? This way or this way, to basically put 5 and 32 together. The exponential way puts a 5 in and gets a 32 out. The logarithmic way puts a 32 in and gets a 5 out. So there's two ways we can basically say the same combination. We can basically do rewrites. We can do essentially what I call conversions. So experimentally, right, I have below here, these are all exponential statements. So how do I change them to logarithmic statements? Well, my base here is 5, so that means the base of my logarithm would also have to be 5. The output is 125, so what's the input of the logarithm? 125. What's the input becomes the output, right? We get that. So in this case, we have 3 and 125 is the input-output. For the logarithmic case, we have 125 and 3 being the input and output. So again, the role reversal is essentially happening. I can say something exponentially, and I can convert it to something logarithmically. The logarithm represents a power that I raise the base to get the number that's inside. All right, or basically I said that. So here the base is 12. 12 squared is 144. So exponentially, I'm saying that 2, 144 is on the graph. Logarithmically, this means I have the log base 12, right, of 144 is equal to 2. The logarithm represents a power that I raise the base to get the number. So 144, 2 is on the graph of the logarithm. Again, there's that flip-flop. You say something exponentially, I can say the same thing logarithmically. So 10 to the negative 3, well, base 10 is our common logarithm, right? We're going to put 0.001 in there, and what's the output? Negative 3, right? So negative 3 becomes the output, 0.001 becomes the input of the log. So they're flip-flopping roles. So here's the exponential statement, its corresponding logarithmic statement, and flipping things around. Fractionally, same thing. My base is 2/3, so the base of the logarithm has to be 2/3. The output becomes the input. The input becomes, oops, that should be a 2 there. The input becomes the output. All right, so we basically have 2 is what I raise 2/3 to get 4/9. So exponential, logarithmic way of saying the same thing. So you're just interchanging places. Here the base is 1/4, so the log would be base 1/4. The output 16, that becomes the input. The input was -2, that becomes the output. Right? So we're flip-flopping input and output. input and output, right? So the base remains the same. The input and the output switch places in the logarithm. E to the 4 equals r. Well, again, the logarithm for e is the natural log, right? So there I am replacing base e. The output becomes the input. The input becomes the output. So e to the 4 equals r is natural log of r equals 4. All right, so we're just basically flip-flopping positions yet again. Again, we got e, so we got a natural log. The output is 14, so it becomes the input. The input was 2x, so it becomes the output of the natural log. So again, we're flip-flopping input and output exponentially to logarithmically. And then last but not least, just in numbers, the base is b, so I have log base b. The output was m, so the input here is m. The input was n, so the output becomes n. Again, we're flip-flopping the ordered pair. So the base is the same, but just in a different spot. Here, the point n comma m is on the graph. Here, the point m n is on the graph. So you're just basically flip-flopping and swapping positions. And the same thing can be done the other way around. Here what I have are a bunch of logarithmic statements. So how do I convert them to exponential ones? Well, the base is 2, so we'll keep that base. 4 is the output, so it becomes the input. 16 is the input, it becomes the output. And I think it's pretty quick, easy to check that 2 to the 4th power is 16. So logarithmic exponential statement, basically its corresponding one. Here the base is 4, so the exponent has base 4. The output's 3, so it becomes the input. The input 64, it becomes the output. And of course, easy check, 4 to the 3rd is in fact 64. Moving right along, right? Log, well, that again means we got base 10. 2 becomes the input. 100 becomes the output. 10 squared is 100, right? That's another way of saying log of 100 equals 2. Here the base is 6. The input's negative 2. And the output is 136, right? Which we know, how do we handle a negative exponent? We rewrite that as 1 over 6 squared, which becomes 1 over 36. So we're basically, again, just interchanging notation from log to exponent and then flip-flopping input and output. Here the base is a half. The output's negative 3, so it becomes the input. The output is 8. So 1/2 raised to the negative 3rd becomes 8. And so forth and so forth and so on. Here the base is e. 5 becomes the input. A becomes the output. So natural log of a equals 5. Exponentially, that means e to the 5th is a. On and on, right? So again, our base is e. The output x plus 1. The input's 32. They should flip-flop positions. And then last but not least, my base is b. The output becomes the input. The input becomes the output. And so there's how you flip-flop that, which kind of coincides with what we said there anyways. So we're just basically saying the same thing in reverse. So one of the nice things is we have two ways to say something exponentially and logarithmically. Just make sure when you do that switch, you keep the base the same and you flip-flop the roles of input and output from exponentially to logarithmically or logarithmically to exponentially. Why is that happening? Because they're inverses. That's what's supposed to happen when we have an inverse. Inputs and outputs flip-flop roles as we change from one inverse function to the other. Okay? It turns out that this skill will help us solve some simple equations, but I'm almost 10 minutes into this, so there's your introduction to the conversion, if you would. Two ways to say the same thing. Now we're going to go see how that solves equations here shortly. New video coming up.